Welcome back to The Explainer. Today we're diving into something totally fascinating. We're looking at a brand new case study titled From Understanding to Resonance: Quantum Music and Embodied Science Communication. Basically, we're exploring how we communicate insanely complex science to everyday people. We're zeroing in on the notoriously tricky realm of quantum physics and checking out how researchers are actually using art and music to completely transform how we learn. It is a stunning look at making the inaccessible, well, totally accessible.
So seriously, how do you teach the unteachable? I mean, think about the last time you tried to wrap your head around quantum mechanics or string theory. If you're like most of us, you probably hit this massive wall of dense mathematical equations, and your head just started spinning. It's incredibly difficult to teach highly theoretical physics to the general public because it's just so far outside our normal daily human experience. But what if the problem isn't the science itself? What if the problem is just the language we're using to teach it?
Okay, let's dive into this. Here's our roadmap for today. First up, the science communication problem. Second, immersive quantum art. Third, 3 dimensions of resonance. And finally, beyond conceptual understanding.
All right, Section 1, the science communication problem.
The friction we're dealing with here is pretty obvious. Public perception treats quantum physics as this distant, highly technical thing that's completely inaccessible unless you literally have a PhD. You've probably felt that exact frustration trying to decode a dense science article, right? But the communicator's goal is the exact opposite. Scientists and educators desperately want their work to be engaging, understandable, and relatable. They want us to share in the wonder of how the universe actually works. But traditional methods, the lectures, the thick textbooks, the endless formulas, they often act as a massive barrier rather than a bridge.
Moving right along to Section 2, immersive quantum art.
So, to tackle this communication crisis, researchers Kenji Noda, Akira Koga, Stefan Heusler, and Koji Hashimoto decided to take some real action. During the International Year of Quantum Science and Technology, they didn't just publish another dry academic paper. Nope, they hosted 2 distinct, real-world international initiatives. They launched Quantum Fest in Japan and Quantum 100 in Germany. And these weren't your typical boring science fairs. These were full-blown artistic experiences designed specifically to see if art could succeed where traditional lecturing was totally failing.
And they didn't just test this out on a handful of undergrads in a lab somewhere. Over 4,000 participants engaged with these events. To put that in perspective, that's enough people to pack a small concert arena. That massive scale is absolutely crucial because it gives the findings of this case study incredible credibility. We aren't looking at some niche anomaly here. We're looking at a widely tested, cross-cultural data set spanning thousands of everyday people.
What's really interesting about this is how they completely flipped the script on education by introducing what they call alternative entry points. Instead of handing people a textbook, they gave them music. Instead of chalkboard equations, they provided stunning visual art. And instead of making people sit quietly in rows, they encouraged embodied participation, meaning actual physical movement and interaction. They completely swapped out cold, intimidating math for warm, sensory, and communal artistic mediums. They literally let people feel the physics before asking them to calculate anything.
Which brings us to Section 3, 3 dimensions of resonance.
When people were exposed to quantum concepts through art rather than math, they moved through 3 distinct steps: sensory immersion, collective embodied meaning-making, and emerging transformative engagement. This brilliantly illustrates the cognitive triad they discovered, so let's break each one down to see how this psychological shift actually happens. Step 1 is sensory immersion. This is defined as using art and sound to completely bypass cognitive overload. You know what happens when you look at a terrifying algebraic formula? A psychological barrier immediately goes up. Your brain essentially goes, nope, this is too hard, I'm out. But music and visual art, they don't trigger that defensive firewall at all. By focusing entirely on the senses, letting you actually hear the frequencies of quantum vibrations or see wave patterns in these stunning light displays, the intimidation factor is totally stripped away. It invites the audience in through a side door that feels safe, natural, and deeply human.
Okay, so once that barrier is down, we move to the second dimension, collective meaning-making. Think about traditional learning for a second. It's usually this isolated individual struggle. You sit alone at a desk trying to force a concept into your brain. But here, learning is an embodied participation where you experience and interpret the science together as a community. When you're physically moving through an immersive art installation with other people, pointing things out, reacting to the music together, the science becomes a shared social event. You're actively making meaning with the people right there beside you, which just dramatically boosts your engagement and your confidence. And finally, that shared sensory experience leads to the third dimension, transformative engagement. Guys, this is the holy grail for science communicators. This isn't just about memorizing some random facts so you can pass a pop quiz. Transformative engagement is an emerging, deep personal connection with the material. The participant leaves the event literally viewing the world differently. They feel this sense of awe and personal relevance to quantum physics that goes way beyond mere academic recall. The science has actually resonated with them on a real emotional level.
And that leads us perfectly into our final section, Part 4, Beyond Conceptual Understanding.
Let's look at these two educational paradigms side by side. The explanation-centered approach is what we all grew up with, right? It relies heavily on logic, facts, and achieving a very rigid conceptual understanding. The resonance-driven approach, which they mapped out in this case study, prioritizes sensory immersion and forming meaningful relationships with the topic. Now, actually, let me be super clear about this. The resonance-driven approach doesn't replace the explanation-centered one. We still need the math. We absolutely need the rigid formulas if we're going to build quantum computers and advance our tech. But this study shows that the resonance-driven approach is a ridiculously powerful complement to it. It acts as the perfect, welcoming gateway for the general public.
The absolute crucial point here is captured perfectly in the study's findings, enabling audiences to form meaningful relationships with science before, alongside, or beyond conceptual understanding. Think about how liberating that is. It proves that you don't necessarily need to be able to solve giant equations on a chalkboard just to connect deeply with the beauty of physics. You can appreciate the symphony of the universe without knowing how to literally build the instruments.
So I want to leave you with this really profound question. Can you form a relationship with science before you even understand it? Well, this massive case study from Japan and Germany overwhelmingly suggests that yes, you absolutely can. By trading equations for melodies and textbooks for immersive art, we can ignite curiosity and wonder first, allowing the true understanding to naturally follow. Keep that in mind the next time you encounter a topic that seems impossibly complex. Just look for the music in it first. Thanks so much for joining me for this explainer. I really hope this sparked your curiosity, and I'll see you next time.